Okay, hello everybody. So today, as promised, we've got lecture slides on hypothesis testing using chi-square distribution. So some of this is going to be what we've already talked about in class, and I think you'll benefit from a second exposure. So let's go through this. Okay, have you ever wondered whether your birthday affects your chances of being a Major League Baseball player or not? Have you ever wondered, do people buy snacks more often for certain movies, certain types of movies, such as a thriller, comedy, or drama? Or is a particular dye fair? And how would you know? Okay, so previously new hypotheses tests required test statistics. These tests require a new probability distribution. This is called the chi-squared distribution. All right, so this is familiar from what we've seen in class. A new continuous probability distribution, chi-squared. All right, and so the notation is, I should have updated this. I want this to say chi-squared, chi-squared. Okay, so chi-squared is distributed, that's what the tilde means, is distributed as chi-squared with the parameter of df. df stands for degrees of freedom. Okay, so the parameters of this probability distribution are the mean is df, the variance is 2 times df, and the standard deviation is the square root of that, 2 times df. The probability distribution, the probability density function and its properties, as discussed, it gets more closer and closer to the normal distribution. So I'll say approaches normal as df goes to infinity. All right. It is skewed to the left. No, sorry, to the right. Okay. And it's different for each df. All right. Now, what is the goodness of fit test? So we talked about the new distribution, which is going to be very useful as we go through these tests, but now let's talk about the test. Okay, so imagine, this is just sort of some setup, some motivating example. Imagine you have data of at least nominal level with finitely many outcomes. So remember, nominal level is you don't have to be able to order it. There doesn't need to be differences. It could just be categorical. So you have a sample of n data points of k different possible outcomes. So an example would be if I was rolling a 4-sided die as pictured in the top corner, and these were the results. This would give me a frequency table. If I rolled it a total of 87 times, I would get this frequency. Now, it looks to me like this might not be uniformly distributed. And so I'm going to do could I do a hypothesis test to determine whether this difference is just random or by chance, or if something is actually wrong with the die and it is systematically, or maybe systemically is a better word for it, systemically giving me bad data, is favoring the 2 for some reason. Or is it just the natural random fluctuations of my data? And so what I will do is do a hypothesis test comparing it to the expected frequencies. Okay, goodness of fit test. Does data fit a discrete distribution? That's what we're talking about. N is the total number of samples. K is the different number of outcomes. O is the list of observed, that's the data. And E is the list of expected or theoretical. Frequencies. Okay, here is the hypothesis test, all 8 steps. So, a goodness of fit test. Does my data fit a theoretical distribution? First thing you do is identify the claim, then you negate the claim or take the opposite of the claim. After that, you identify the null and alternative hypotheses. The null hypothesis, H naught, is that the distribution of given data is as suspected. Now, I just want to say, it's not that the distribution of the data is suspected. It's that the underlying process that generated that data has a distribution as suspected. See, we know the distribution of the data. That's written, and it's clearly not, in this case here, it's clearly not the same as this. The frequency of the data is not the same as the expected. But is the difference in the data sufficient to suggest that the actual theoretical underlying process that made that data is flawed? That the actual process from which the data was sampled does not have the expected frequency? That's what we're asking about, and I sort of wrote that in a bad way. It's not about the distribution of the data, it's the distribution of the generating process of the data. Okay, so that if I took another sample, it would be different, and would that be closer to the suspected distribution? All right, the alternative hypothesis is that the distribution is not as supposed. Okay, now, you'll notice these chi-squared equals 0, chi-squared greater than 0, because, as was noted in class, the chi-squared statistic, which we will introduce in step 5, is a measure of how different the data is from expected. So as a measure of how different expected is from observed. So if we say that chi-squared equals 0, that means that the data completely agrees with suspected, completely agrees, and that would suggest, as best as anything could, that the underlying process agrees with the suspected. Okay. The alternative is going to be chi-squared is greater than 0. Notice that chi-squared will never be negative. So we don't need to entertain that possibility. And so the opposite truly is just that chi-squared is greater than 0. Step 4, as usual, select significance level. Step 5, identify test statistic. Well, what is the test statistic? It's given to you. It's this chi-squared test statistic. And we'll go over how that is to be calculated in the example. Next, step 6, as always, find the p-value. In this case, the p-value is always going to be right. It's always going to be a right-tailed test. So you use a chi-square distribution, which we just talked about. But wait a minute. Chi-square distribution needs degrees of freedom. What are the degrees of freedom? Well, it's going to be k minus 1. All right. After you have found the p-value, you have to make a determination. Is that p-value less than alpha? If the p is low, then the null must go. If it is not, then we fail to reject the null hypothesis. Then we restate the decision in non-technical terms with reference to the original claim. There are requirements that ought to be met before you proceed. Make sure that the data is random. You have no guarantees about the theory to follow, the conclusions to follow. You have no guarantees if the data is not randomly selected. If it's very biased, if it's very poorly collected data, then the theory that we're going to discuss won't apply. And the second requirement is that the data are frequency counts of a set of outcomes. And of course, we wouldn't be able to calculate anything if that weren't the case. Okay, and then for each outcome, the expected, not observed, but expected frequency has to be at least 5. Okay, let's go over this example, which many of us are familiar with. And if you feel good about it, you may skip a few minutes and go on to and answer a few cues. All right, but if not, and you want to see it again, then follow me. So this is my spreadsheet that has the data, and a spreadsheet exactly like this one can be found on the Canvas home page for our course. All right, let's go ahead and insert something. Let's clean this up a little bit. So there's my data. You know what, actually, I'm just going to leave that data up there. Let's go ahead and start our hypothesis test. Well, let me read the question. All right, absenteeism of college students from math classes is a major concern to math instructors because missing class appears to increase the drop rate, which is very unfortunate. Suppose that a study was done to determine if the actual student absenteeism rate follows faculty perception. The faculty expected that a group of that should be 500. I forgot to change that. 500. A group of 500 students would miss class according to this table. This is what was expected. So about 250, about half of them would only miss 1 to 2 classes. 150 of them would only miss 3 to 5 classes, and so on. Okay, so, and then a study was done, and 500 students were randomly selected, and their absences were computed, were found from data. Test the claim that the faculty perception is accurate. Okay, let us do so. So we do step 1. Oh, wait, come on now. Oh, save a copy. That's right, save a copy. Save, great. Step, okay, there. Step 1, original claim. Well, the original claim is that the faculty perception is accurate. Now, I always want to write that just as I see it in the problem, because that original claim is going to guide my step 8, which is reporting it, and I want to report it as close to the question being asked as possible. That's just good policy. When somebody asks you a question, you want to give the answer in as much as their words as you can, so that you make sure you answer it as faithfully as possible. All right. The opposite of the observed claim is going to be that the faculty perception is not accurate. Is there just one C in accurate? I wish Excel had I wish PowerPoint had a spell check. I'm afraid I need it when I'm doing these videos. Okay, anyway, well, you'll have to forgive me if I spelt it wrong. Okay, now, as we talked about, this is equivalent to chi squared equaling 0. So the faculty perception. So the actual chi squared, the actual chi squared, right? When we talk about hypothesis tests about mean, we're not talking about the data. We're talking about the actual mean. The actual chi squared is going to be 0. That's the original claim. The alternative to that is that the chi-squared is greater than 0. Okay, let's go on to step 3. And our null hypothesis is going to be, null hypothesis is going to be that the perception perceived frequencies, and this is in general, right? The perceived frequencies agree with the actual absentee frequencies. H1, the alternative of that is that they do not agree. Okay, great. Great. Okay, so now let's go to step 4. And this is going to be alpha. This is significance level. Alpha equals, I don't think a significance level was offered here. Okay, so what's that going to be then? 0.05. Step 5. Step 5 is the test statistic. See? Step 5, test statistic. Okay, so what do we do here? Well, we're going to do test. All right. Statistic. Okay. So I need expected. No, I need observed, and I need expected frequencies. Now those are given here. Oh dear me. Let's see, Control Z. Let's see. Yeah. All right. Oh dear. Control Z. Okay, good. All right. I don't know why. There. Command C. Command C. Now, are these observed, or are those are the actual? So those are the ones that were observed. So that Command V. Paste that. All right. And now these are the perceived. These are the expected. Command C. Come over here. Command V. Great. So those are copy and pasted, I guess. Now this right here is going to be my E minus O, or O minus E. Not that it matters because I'm squaring it. Squared divided by E. And that's what I get here. Equals parenthesis O minus E quantity squared divided by E. Enter. All right. Command C. I copied that. Shift. Down. Command V. Paste. And this is going to be test statistics. So I'm going to say chi-squared equals this. And this is going to equal the sum. So I summed up for each outcome. All right, enter. There it is, 96.37, which is enormous, just enormous. So these are wildly off. Okay, but anyway, let's just carry on for demonstration's sake. So step 6 is Step 6 is now to compute the p-value. So the p-value is going to equal equals, let's see now, chi, right? Chi squared dis dot rt. Yeah, I think that's what I want, dot rt, because it's a right-tailed test. It's always a right-tailed test. Now for the x, I'm going to push chi squared. For the degrees of freedom, I'm going to do k minus 1. And in this case, k is 5. There are 5 different outcomes. So my degrees of freedom is going to be 4. Enter. Yes. Super small, as I suspected. So step 7 is to make... okay. Step 7 is to make my conclusion, make my determination, and is the p-value less than alpha? Yes, very much so. So I reject that null. I reject the null. Okay, step 8. What do I say then? My original one is that original claim is that faculty perception is accurate. All right, so yeah, I rejected, so there's sufficient evidence. So I'm just going to start with that. There is sufficient evidence to conclude. Now, the null hypothesis was that the null hypothesis, not necessarily the original claim, but the null hypothesis was that the perception agreed with the actual, which happened to be the same as the original claim. We rejected that null hypothesis, so we rejected the original claim. So there is sufficient evidence to conclude, well, let me go like this. There's sufficient evidence to warrant rejection of the claim that faculty of absenteeism is accurate. There's sufficient evidence to reject that claim, which was the null hypothesis, which we rejected. Alrighty, so there it is. There's all of our steps. That's our hypothesis test. So something that looks like this is what you're going to want to give me on the exam, nothing less. And make sure that I am able to push on all of these and, to select each of these cells and see the formulas here. I want to, how is the p-value computed? See, I can click on it and I can see exactly what function I can use. You will get very little credit if I push on that and it just shows me the number, like you wrote it down somewhere, copied and pasted it from something. So don't do that. I want to be able to see your formula. Because I want to know what you're doing wrong if you're doing it wrong. All right, very good. Okay, that's great. Okay, so that's that. That's the absenteeism one. The faculty perception is not accurate. Okay, now at this point, go ahead and fill out these questions, please. I'll be looking on the slides. If these questions are not answered, you will lose points. I want you to try and answer those. Okay, now I want to say just a few words about a very interesting phenomenon, Benford's law. The observation that the leading digit, that's the leftmost digit, numbers have a leftmost digit. The observation that the leftmost digit in real-world data follows the following distribution to the left. That's what Benford's law is. It's very interesting how that just sort of happens. So basically what it's saying is that numbers with a leading digit, LD, of 1 occur with a frequency of 0.301. That's 31.3% of the time. So of your data set, you can expect about 30% of those numbers to begin with a 1. Isn't that something? On the other hand, numbers with a leading coefficient of 8, say, generally occur only 5.1% of the time. So in your big data set of numbers, you can expect that they will begin with an 8 about 5% of the time. Isn't that something? This phenomenon is so well established that it is used to detect fraudulent data. So data that has been doctored, fraud. Okay, let me concentrate now on spelling this word. Fraudulent. Okay, fraudulent data. So data that has been doctored, that has been changed in an individualized way, will violate this Benford's law phenomenon, and that can be exploited. And here's an example now. In the New York Times article following Benford's law and looking out for number 1, Malcolm Brown writes that, quote, the income tax agency of several nations in several states, including California, are using detection software to identify computer system intrusions based on, and this software is based on, Benford's law, as are a score of large companies and accounting businesses. So Benford's law is out there. People are using it. All right, anyway, we're going to do a Benford's law example at the end of this slide deck. Okay, but before that, I want to introduce another hypothesis test. This is called a test for independence. Do the variables affect each other? Now, here's the setup. So you have a sample. You have so many subjects. And what you do is you look at two variables. So you have a sample of categorical variables from n subjects. So such as two variables could be race and income, or gender and employment status. And then what you do is you make a contingency table. How many subjects are in a particular gender and how many have a particular employment status? And you make a contingency table. Race would be on one, maybe race would be row labels, and income classes or categories would be on the column headings. And you have a contingency table. You count the number of people that fall into both categories. Then what you can do is you can test to see if one of the variables has an effect on the other. Okay, so is a particular race likely to have a higher income? That means that it affects it. It's not independent. So there's a dependency there. Okay, and so the question is could the variables be statistically independent of each other? All right. So a test for independence has some notation, which we'll go through right now. N is the number of samples or subjects. R is the number of categories. Or the number of rows, which is the number of categories in one variable. C is the number of columns, which is the number of categories in the other variable. You have a two-way table. O is the list, which is an array in this case, of observed frequencies. And E is a list of the actual empirically determined expected. No, sorry. This one's empirical. This one here is more or less theoretical. And that's the expected frequencies. Now, how do you come up with these expected frequencies? How do you do that? Well, here's what you do. You take so each E is going to be associated with a particular cell for each cell of the table. Now, each cell is in a row, is in its own row and its own column. And so what you do is you take that row's sum, so the row total, you take that row total and you multiply it by whatever the column total that it is in. Multiply it by the column total for that cell. And then you divide by the grand total. And that is your expected frequency for that cell. All right, let's take a look at that. Okay, and so that is how you find the expected. More on that later. Okay, test of independence. Do the variables affect each other? That's what we want to know. Okay, so again, you identify the claim, you negate the claim, you identify the null and alternative hypotheses, and what you do to do that is the null hypothesis is always going to be variables are statistically independent. We assume that they are independent, that there is no difference between the expected, which assumes independence, and the observed. And so chi-squared for that is going to equal 0. The alternative of that is that they are not statistically independent, and so chi-squared would be greater than 0. And again, this is not chi-squared using the data. When I write it here, I mean chi-squared of the actual sampling process, the variable, the true variable that I'm trying to process, the true distribution of income versus race. All right. Step 4 is to select the significance level, and step 5 is to select the test, to identify the test statistic. And it is exactly the same as with a goodness of fit test. The only difference is that a goodness of fit test only had K categories. This one here is going to have R times C categories. You're going to have a term in this sum for each cell in the contingency table. Okay. That will be clear. You will see that very clearly in the example that we do. Next, you find the p-value. It's always right-tailed. In this case, though, the degrees of freedom is going to be r minus 1 times c minus 1. After you have the p-value, you need to make a determination. If the p is low, the null must go. Following that, you restate your decision in non-technical terms. Okay, now, of course, in order for this to apply, the data must be random. Randomly selected. You need to take your sample, make your sample very carefully. And then, of course, the data needs to be in a contingency or a two-way table. Now, for every cell in the table, the expected frequency must be at least 5. Again, we don't want to deal with rare events. Okay, now for the example. Suppose we collect data from 600 people at our theater, at a particular theater, say. For each person, we know the type of movie they saw and whether or not they bought snacks. Test the claim that whether or not a person buys snacks depends on the type of movie. So in this case, we have got two variables. A binary variable, did you buy snacks or did you not? And a categorical variable, what type of movie did you watch? Action, comedy, family, or horror. And the question here is does whether they bought snacks depend on what movie they watched? Were they more likely to buy snacks for an action movie or a comedy rather than a family or a horror movie? That's what we want to determine. We want to do it in a principled, sophisticated way. Okay, and so what we're going to do now is I'm going to get out my keyboard and we're going to go into Excel. We're going to work this problem out. Okay. Snacks. So I go to example 2. All right, step 1. Original claim. What was that again? Whether or not a person buys snacks is depends. Okay, so depends on the type of movie. So the original claim is that there is dependence there. Okay, so the original claim is whether or not, a person buys snacks. Depends on the movie they see. All right. Or saw or are about to see. Take off cap lock. Sorry, I accidentally did that. Okay, step 2. Now I guess I'm in the habit of symbolically writing this. So I say chi² equals 0. That's the symbolic notation for no. No. Excuse me. We are assuming that they are dependent and that it does not behave as we would expect if it were random, if it were independent. So in this case, my original claim is that chi² is greater than 0 because it surely can't be negative, but it's not 0. The opposite of the original claim is this. Whether a person buys snacks or not doesn't depend on the movie. Go ahead and leave it at that. So this is saying that they are behaving as though they are independent. Their choices of snacks and movies are depending as though as though they were independent. All right, step 3 now. The null hypothesis, as always, for these types of tests, it is going to be chi² equals 0. And so the original claim, so the alternative hypothesis is again going to be chi² is greater than 0. All right. Step 4. And so this would be that the two variables are independent. That is my null hypothesis in English. The two variables are not are dependent. And I'll say this is statistically dependent. We can only talk about it statistically being independent or not. We don't really know if they're affected, actually. Okay, so step 4. What's step 4? Step 4 is alpha. Alpha equals 0. Oh no, does it? I don't think it said. Did it? Did it say? No, it didn't say. 0.5 again. 0.05. Okay, great. Step 5. Okay, now this is what you've all been waiting for. Step 5. I need expected. So, well, first I'll do observed. So observed equals, okay, now it's going to be this table right here. Command C, come over here, Command V, all right? And now the expected is going to be here. Okay, now actually, I want to, maybe I go over here. Expected, E equals. Now the reason I saved space is because I'm going to want the row totals and column totals. And so here's what I'm going to do. I'm going to do row totes. That's the row totals. This here is going to be column totes. Column totals. Okay, so I'm going to go equals sum, like that. Enter. Okay. Command C, Shift over, Command V, there. Now this one equals that. Well, I could just do that plus that, couldn't I? There. Equals that. Didn't even need to use the sum. Command C, whoops. Command C, Shift, down. Command V. And it said that there were 600 moviegoers, at least I think it did. Yeah, 600, so that's a good check. That right there, that box that I have selected now is going to be the grand total. All right, now let's find the expected distribution of this table. Now, it is going to equal the particular row total times the column total. See, so I'm in this first cell now. This first cell is going to correspond to the 50 here. And then I'm going to divide by the grand total. Now, I need to put in some dollar signs here. So as I move my table, as I fill my table, I want the row total referenced not to change when I change my column. Because if I only change column, it is in the same row and therefore has the same row total. So I don't want to change the column. The column is indicated by the letter. So I'm going to put a dollar sign in front of that letter D so that the letter does not change. Wait a minute, hold on. If the column changes, if the column changes, I don't want the column to change. So I'm going to go D, just as I thought. I kind of second guessed myself. Okay, now when the row changes, I don't want the column total to change. I don't want that to change, so I'm going to fix that column. However, I do want the column to change if I change columns. So this B24 is my column total. And if I move this cell that gives me the expected frequency, if I change cells to a different column, I want that column total to change. Similarly, if I change rows, I want the row total to go to a different row. So I'm not going to put a dollar sign in front of the 20, which tells me the row. And so I'm not going to put a dollar sign in front of the B, which tells me the column. But I will put a dollar sign in front of the D and the 24 in this case, because I never want the grand total to change. Okay, take a hard look at that. This is complicated stuff. Okay, equals. And there is my expected value for the first cell. Okay, great. So now here's the beauty of it. Command C, I am going to select all of this. Command V, and there's my expected frequencies. Okay, now let me just Command C and bring this over. Command V. Okay, so there's my row and column sums. Okay, and now what about these here? Equals this plus this equals, okay, 125. Command C, paste, and V. Okay. Let me just, oh, wait a minute, oh, that's wrong. Okay, Command C, Command V, Command V, Command V. 600 again. Okay, see, so that gives me an indication that I did it right. So the grand total is always the same. It just tells you that if they were independent, this is the most likely arrangement for them. All right, so there's my observed. Go ahead and put a border around that. And here's the expected. Put a border around that. All right. Now, what I need is, and I'm at a loss of words to put this. I'll put this right here. This thing is going to be my O minus E squared divided by E equals, and that's going to go in this table here. Okay, I'm going to go equals, parenthesis, O minus E, close parenthesis, quantity squared, divided by E, right there. Okay, and I'm going to be copying, I'm going to be filling this all around, and I want all of those cells to change as I change which cell that is housed in. That's in. I'll enter. Okay, so no dollar signs there. Command C. Fill all that in. Command V. There's all of the sum of the differences. The sum of the square of the differences divided by the expected. All right, and so my test statistic then, chi-square, is going to equals the sum of all of this. All right, and it's 65, which is quite high, but the degrees of, yeah, that's really quite high, especially because the degrees of freedom is going to end up being 3, I think. All right, I'm so glad you guys are, this is a video, so you can go back and look at all this. I sure hope the way that we determined E and the chi-squared statistic makes sense. Please feel free to come into office hours if it doesn't, and we'll just talk about it until it does. All right, step 6 now. I've got my test statistic. Step 6 now is to find my p-value. Okay, so the p-value is going to equal, well, this is fairly straightforward in comparison. So equals chi-squared, right tails, always right tailed. Push my test statistic right there, comma. Okay, now the degrees of freedom. Actually, let me do this. Let me do degrees of freedom. df equals, this thing is going to equal the row count, which is 4, the number of rows, equals 4 minus 1 times 2 minus 1. So the number of rows minus 1 times the number of columns minus 1. And that gives me 3, so that's my degrees of freedom. So my chi-square distribution is going to have a mean at 3, and this is 65. So this p-value is going to be way, way small. And so there it is. So step 7, step 7 is p value smaller than alpha? Is the p-value smaller than alpha? Yes, it certainly is. And so I reject the null. Step 8. Step 8, what was my original claim? My original claim is that whether or not a person buys snack depends on the movie they see. Now, that was the original claim, but that was not the null hypothesis. The null hypothesis was the other one, was that it does not depend. So what we see here is that there is certainly some dependence going on here. It doesn't give us any insight as to what that dependence may be, but to say that they're independent is a statistical absurdity. It's with probability 4.9 times 10 to the negative 14th. So if we ran this experiment, like 100 trillion times, if we ran it 100 trillion times, then one of those would be what have I got myself into? One of those would be, let's see, so the probability of it being, one of those would not be considered extreme. Out of 100 trillion. Otherwise, it's always going to be extreme. So, but the original, so what that means is we rejected the fact that they are independent. So what we're going to say is that there is sufficient evidence to suggest a dependence on whether a person purchases snacks and the movie they see. All right, great. Okay. All right, let's go. Let's go to the next thing now. All right, so there was a dependence there. Here are a few more cues for you to answer. Again, I'll be looking at these. Interested to see what you have. Okay, now this is the last test that we'll be talking about. We're nearly done. So, test of homogeneity. Do two random variables have the same unknown distribution? So we've got two discrete random variables. Do they actually have the same distribution? All right, so here's an example. Do males and females live in dormitory apartment or with parents at pretty much the same rate? Or do they not? This is exactly the same as a contingency table test. Just the interpretation's a little bit different. Okay. So, test for homogeneity. Do two discrete random variables have the same unknown probability distribution? All right. So the interpretation is a little bit different, but the way you do it is exactly the same. All right. So anyway, could the distributions possibly be from the same population? All right. N is the total number of samples. R equals 2. There's just going to be 2 in this case, and that's the number of rows. So I always think of that, each population has its own row. C is the number of columns of this. There may be many. O is the list of observed. E is the list of expected. And again, the expected value for each cell is going to be the row total. So the each cell is in a row. The total of that row goes here. Each cell is in a column. The total of that column goes here. No cell is going to have the same row or column table. This number is unique to a particular cell. And then here we have grand total. All right. Here's the test for homogeneity. Exactly the same as the test for independence. It really is. Everything else is exactly the same. I copied and pasted it just and changed nothing. All right. Again, the requirements are exactly the same. The data needs to be random. The frequency counts need to be a part of a contingency table. And the expected frequency must not be less than 5. Here's the example. This is used from actual data that I got from the Pew Research website. I'm beginning to use my own data now. Well, that I get myself. Okay, example 3. Is there a political right and a left? Okay, is a Friday form... in a Friday forum, goodness, it was suggested that the political right and the political left is in some sense a myth. So they said, the myth of the left and the right. One way of looking at this is to test whether those who self-identify as either right or left actually feel the same about certain issues. So if on average they feel the same about certain issues, then there really isn't much of a difference between them. And that supports this idea that there isn't a right and a left. This is not exactly what the speaker meant, I believe. I think he just said that rather than there being one spectrum, one dimension in which you can neatly divide people, there are a multitude of dimensions, and this doesn't exactly speak to that. But it's an interesting question nonetheless. Okay, so the data below is from a Pew Research study from 2021. When asked the question, how would you rate economic conditions in this country today, the following responses were observed. Okay, so 10 people who self-identified as being from the right said excellent. 329 said good, only fair was said by 996 people who identified as being from the right, and so on. All right. So the tests that claim that the distribution of sentiment is actually the same across the political spectrum. Okay, let's take a look. Let's see if the p-value is going to be, if the test statistic is going to continue to be super big. What do I do now? Okay, tab, there we go. All right, so now I go to right and left. Okay. Step 1. Okay, we'll just go back to it. What was it again? A test that claimed that the distribution center is actually the same. Okay, so, okay, so the same. So the distribution of the sentiment of the distribution of the perceived strength of the economy that doesn't seem right. There it is. Does not depend on political ideology. Okay. Political ideology. All right. And if you don't mind, I'm just going to copy that, Command C. Okay. Now I'm going to do step 2. Command V. Command V. Oh, it didn't work. That's okay. I need to go in here and put OC anyway. Original claim. All right. Now I'm going to copy this cell. Okay. Come here. There it is. Now this is the opposite of the original claim. Distribution of perceived strength. Oops. Too many THs. Of the economy does depend. That's the opposite. Does depend. Okay. And so again, this one here is going to be chi-square equals 0. This one's going to be chi-square is greater than 0. Step 3 is what? Step 3 is the null hypothesis is going to be chi-square equals 0, which basically means in independence, or they're homogeneous. These are homogeneous distributions. Meaning the distribution is shared. And then chi-squared is the alternative is that it is greater than 0, and so this is dependent, meaning that they are not dependent, meaning they're non-homogeneous, not the same distribution. All right, step 4 is alpha. I don't think this is alpha given this time. Nope, 0.5 again. 0.05, I mean. All right, step 5. Okay, great, cool. Let's come up with this. So this is going to be the test statistic. All right, so we need observed, and those are here. Okay, then I'm going to need totals. So column totals and row totals. So equals sum of all of that. Enter. Okay, Command C, Shift over, Command V. There's the paste. Okay, now this thing equals, I'll just go sum, this, and that. Enter. There's that. Command C, Command V. Let's go one more. Command V. There. Okay, so there's 8,468 people were polled by this Pew Research study. All right, now let's compute the expected. So here's the original data, and I'm going to be filling in this box of expected data. All right, this thing is going to equal the row total, but the row total times the column total divided by the grand total. Now let's put in some dollar signs so that I can fill it, and the appropriate things will change. Okay, so the row total, I want that to change if I change rows. I don't want it to change if I change columns. So the column designation, which is D, must stay the same. Now the column total, I don't want it to change when I change rows, because it's in the same column if I only change rows. So I don't want it to change if I change rows. The row designation is the number, so I'm going to put a dollar sign in front of the number. Now the grand total, I don't want it to change at all. So I'm going to do just like that and freeze that whole frame, that whole cell. Enter. Okay, there it is. Command C, copy that. Fill all that in. Command V, and there it is. Okay, now let me just take some, let me just do this. Let me just test the grand total here. Equals sum of them all. Perfect. Okay, that's looking pretty good to me. All right, now over here is going to be O minus E squared over E equals, okay, and I'm going to go equals O minus E squared over E. Enter. There it is. Populate, whoops. Oh, okay. Command C, Command C. 4 columns, 2 rows, Command V, and there it is. So that's all those differences. And so now my test statistic is going to be chi-squared equals, oh, and it looks like it's enormous. All right, I need some better examples, ones that are maybe even closer to the same distribution. Okay, equals the sum there it is, 299. It's very big. It's very big. Yeah. Wait a minute, something was wrong here. Oh, no, I don't. Oh, no, that's exactly what it needs to be. That's funny that it's the same numbers. Huh. Yeah, very strange. Okay, anyway. All right, so there's that. Now let's go step 6. P-value equals, okay, let's compute the p-value, which I already know is going to be ridiculously small, but I'm going to do it anyway just so we know how to do it. We need practice, right? We need practice to really learn how it's done. So I'm going to do equals, what do we do again? Chi-squared dot dis. There it is. Put that in there. Degrees of freedom is going to be 3 again. And this is going to, okay, 3 and enter. To the negative 64th. Whoa, yeah. That's small. Step 7. P-value less than alpha. Oh, yeah. Yeah, it is. Reject the null. Step 8. There is sufficient evidence to suspect. There is sufficient evidence to suggest that, let's see, what's the original claim again? The perceived strength of the economy does not, does depend, to suggest that the perceived strength of the economy does depend on political ideology. All right, very good. Okay. What do I do with that now? Go back to Notability. All right, just one more cue, and then there's the 2 more examples that I have. Oh, both. Oh, what? Oh, my word. Okay, well, I had a different example there. Anyway, yeah, feel free to stick around for the... Okay, so I'm going to go ahead and end this video now, and I'm going to do the example videos later. Okay, everybody, have a wonderful day, and good luck.